Hello, everybody. This is Mark Kersner here, the presenter. I just want to make sure, confirm that we are on and that you can hear me. Yes. Okay, great. So let me share my screen now. And for that, confirm that we are looking at my slides. Excellent. So here is what I want to talk about today. I want to tell you about machine learning and AI, which stands for artificial intelligence. The whole presentation, I hope, will be interactive in the sense that you will be asking questions and that you will be also participating in the discussion. I do not want to just talk at you all this time, but I want to bring you useful information on all these topics, which are, by the way, the hottest topic. Here's what we want to do. We want to see what is the potential of this machine learning and artificial intelligence, and go a little bit deeper, explain what this machine learning is, how do you use it in your projects, how do you use it in your work. So let me interrupt this slideshow for a second and just look at Google Trends just to see what's going on in machine learning. So let's say we go to Google Trends and I'm opening my browser, going to Trends, Google, and let's put machine learning here. So let's do machine learning. Okay. So what we see now is that there are about 75 units. We don't always know what is a unit, but we see that it is a significant amount at least. Let's do artificial intelligence. We should see them pretty close because those are two very hot subjects. If we go down, we'll see that here they are, that the major interest in machine learning is all over the world, and AI is particularly prominent here in China, which agrees with the fact that China is very strong in artificial intelligence and that there is an actual arms race between Russia, China, and the US. But for comparison, let's do something more prosaic like IoT, and let's see where that IoT would come in. Well, IoT is just as hot. So we see that these are the popular areas. Well, what about some mundane topic? I completely improvising. So it turns out that car buying is kind of on the bottom, even though you would expect it to be way above. So that itself tells you that yes, we are dealing with some very hot subjects here that people are more interested in than in their daily lives. So therefore, let's continue and look at what that subject is. So that is the machine learning from our cartoon illustrator, but we'll get a bit deeper. First of all, we'll talk about what this machine learning is, and that is the founder, the guy who invented the term machine learning. And he said that is an area of computer science, which everybody agrees, that allows the computer to learn from data instead of you giving it all the rules. So I'll give you one example. Let's say we're building a self-driving car. Well, one way is to analyze the rules. Here are the rules. You see this object, you turn to the right. You see the traffic light, you stop. So you could write dozens, hundreds, and thousands of such rules. But a different approach would be to put this computer in the seat right next to you, connected to your senses, connected to the reactions that you do, and also give it the way to see what's going on around. And then next step is we don't give computer any rules. We're just saying, here is the situation. You figure out what I would do in this case. So learn from my behavior. I'm giving you 50,000 hours of my or somebody else's driving the car, and you figure that out. So that would be one example of how an example of machine learning by itself rather than I'm giving it all the rules. There is another definition, a more modern definition, which says not only it learns from the rules, but it becomes better and better at what it does. And here we have some of the letters introduced. We're saying that E is the experience, and that the task is what we're asking the computer to do, and that the P is the performance measure, and there should always be one number, how good that computer is at what it's doing. So for example, if we're saying that we're trying to make the computer talk, not necessarily talk in speech recognition, that is part of that, but mostly making intelligent answers. So E would be in that case the experience of running many dialogues, and C would be the task of trying to talk like a human, and P would be that one number where we have fooled the humans and we made them think that we are not a computer but a human. So that would be a more precise measure. What's important here is this number P. P is always a number and it should be a single number. In other words, given this experience E, and the model that I come up with, the model that learns from my behavior and that makes the computer behave exactly as I would, or maybe even better. So I need that one number P that will make sure that we are behaving well. For example, let's say we're doing face recognition. So we want to know how many times we recognize the face correctly. And maybe we had a few million faces and we mislabeled, let us say 100,000. So we are somewhere in the 98% range. That is good. Human rate of recognition is somewhere between 95 to 98. So we can get there. This is good. Therefore, now we understand that we make a computer, a machine learn from experience. We also have measures on what all of that means. The next step is let's formulate this. And the one technical subject that will come up, and people say raise this ugly head, but that depends upon how you view mathematics, is that very often people need to know linear algebra with the most simple things like matrix, determinant. So why is that important? And do you need it? Can you do without it? The answer is that technically you do not need it. All of the providers of machine learning, and I will talk about them later on, all of these providers are trying to hide the mathematical complexity from you. To a certain extent, they succeed, but it does help. So let's see, why would it help? That is because you will be thinking in terms of features. For example, let's say we're trying to learn the house price. We're trying to find out how to predict in the best possible way what can I sell the house for. So what I should look at is the square feet in my house, but maybe also the garage, the presence or the absence, how big the garage is, how many bathrooms, is there a lot, how big is the lot. So all of these will be numbers, and all of these numbers will form a vector together. That's where algebra begins to come in. If I then collect all of my vectors, each individual vector describing my house, if I can collect all of them together, that becomes a matrix. Well, it turns out that if I can formulate the problem in this way of matrices, then first of all, the formulation is very short. But more important is that the solution is very short, and therefore it can be parallelized and optimized, and it can run thousands of times faster. That's why deep inside, it's good to understand math. I've seen a couple approaches. One of them tries to show as much math as you possibly can, but then says, well, if you didn't get it, that's okay. And another one just ignores that, and I believe that it's a good introduction, but to make your models really work, to make your car drive in a consistent way, to recognize those faces, you do need to know something about what's inside. Well, regardless of if we understand that on the level of I can do it, or on the level I know what it gives us, we are all in use of machine learning and intelligence. If we look at the history, we'll see that It all started in the 60s with sometimes more promises than it could do, and sometimes surprisingly it was coming back. And what changed was 21st century. Here's what happened in this century. If you look at all of the machine learning methods, and here in green I show approaches other than neural networks. Here in the blue, I'll show just the neural networks, and later on we'll explain what is the difference between those two approaches. Then you will see that neural networks have an awesome potential, mostly because they are looking at all of the details of the data, whereas all other methods try to more or less average them out. There is still a lot of applications for other approaches, but neural networks, when we're talking about most complicated tasks like scene imagery analysis, face recognition, talk recognition, that's where usually you'll find neural networks. So in the 80s and 90s, the amount of computation that we could do would put us only here, so we could only perform to a certain level, and other methods then worked better. Then we got more and more compute power, and suddenly, boom, what happened is that our computing power became more. And at this computing power, our neural networks became better. And now that is why that's the final step in all of machine learning. We are going with neural networks if we can, because they give you more precision. That is exactly what happened. And with that, AI began to outperform the expectations. Unlike previously, it was more expectations than it could do, and it could deliver. Now it is more delivery very often than expectations. So that is why this red line shows you what exactly happened. So let's look at what's going on today. First of all, in the world of neural networks, there is a certain library. That library is called TensorFlow, right here, TensorFlow right in the middle. That is the open source library designed by Google. And it is the very precise library. Besides, it is supported by Google. So it's very popular. If you look on Google Trends again and measure the TensorFlow, you'll see today the library itself beats all of the other libraries. But the hardware, that's not such an easy thing, because with TensorFlow, you need a powerful computer. So most people can manage a powerful computer, and that's how most people use it. Google has one advantage over there, is that they also have a scalable TensorFlow. That's not all that easy. That's the second step, and for that you might want to go to Google Cloud. That's one of the advantages of Google Cloud. Well, deep inside, it's not just the library. It is also that Google said, well, could we create hardware that would be able to implement this? Just as there was an idea of Bitcoins. Can I create special hardware just to do Bitcoins? So they created special hardware to do just the TensorFlow. And with that comes the TensorFlow processing unit, TPU. That's what it looks like, and that is available to universities, researchers, and I think very short while ago it became available to all of the regular people as well on the Google Cloud for a price, of course. So this is where the state of the art is today. Now let's go and look at precisely what this machine learning, what this artificial intelligence can give you. Here are the use cases. The credit card fraud. There are quite a few parameters of what makes a credit card transaction unusual and what makes it run-of-the-mill transaction. And by now, I think we all know that the leaders in the space, which is Visa, American Express, all these guys use huge clusters. They use machine learning to find a way how to detect unusual transactions. And sometimes you may travel to a foreign country, and that's still okay. That's within the limit of what they would expect you to do. But sometimes it may come from deep down a small town in Texas, and that's not okay, and that's not what they expected you to do. So that works pretty well. Recommendations, they form the heart of almost every website now, and recommendations present their own problems because you might have millions of products hundreds of thousands or millions of users. So here too, we need to do precise recommendations, something that would work for that particular user. Another interesting case is genome data manipulation. People can detect diseases. They can sometimes perform better X-ray analytics than humans. So computers are great there too. And how does it happen? So we see the use cases. We see that many people are able to run those amazing use cases. Well, the way it happens is this. There is this overall broad area of artificial intelligence. And that artificial intelligence includes everything that computers are doing today. It's not such a precise boundary because a long time ago, when computers just became alive, then they were doing something that was always thought in the domain of humans, and that is they were crunching numbers. So today we feel that's not AI, that's regular thing that computers can do. But very soon, other tasks follow. For example, if the computer recognizes faces, then very soon you will say, well, that's what the computer does. It's not really AI. It's not something unusual, or at least your understanding of AI changes. So that is an area where the computer does things which are usually considered smart. Well, as I mentioned, gradually they become normal and not so smart, or they are smart, but they're not at least any artificial intelligence. So within that very broad area, we have machine learning, and that is all of the methods that I will show you. For example, linear regression. Sounds complicated, but all it does is, given the certain amount of data, it tries to predict what would the next point be, or what would the next price of the house would be. That is the machine learning in general, and in particular, there is deep learning, which deals with neural networks, which deals with this sometimes TensorFlow. That's something that takes, let's say, when I teach a course, maybe it is 3 days. When you become a practitioner, then I will tell you how long it will take. Here is this neural network explained. A neural network as a technology is modeled after human brain. And just as human brain can recognize patterns by randomly connecting those cells inside the brain and then reprocessing the signals. Let's say you look at something, those light signals go through the 100,000 of cords on your eye, then they end up in the brain, and that is what processes all that information. So you can try to build a similar system of neurons. They're called artificial neurons, and you can then try to make sense out of that based on the output that you should have. So neural networks appeared in the 60s, and then they were felt like that's not the direction to go. The direction to go was logical artificial intelligence that would convert everything into symbols and try to deal with symbols. Well, it turns out that this was because we didn't have enough data to train and not enough compute power. So that all changed, as I told you. There is one interesting thing is I don't think that replaces a human brain, because by now most people don't think that this is how our brain works. That was a good model to start with, but it's too simplistic. A human brain, I think, has either 100 million neurons or a billion, and that's where the computers are in size. But in a human, every neuron seems to be like it's another brain. So every neuron is very smart by itself, which is not true about the computer. Okay, so in any case, it works even though it doesn't explain often how it works. Here is an example of what happens when we put in raw data and we begin to go through layer after layer of conversions, and gradually we begin to see small features and bigger features, and altogether that makes a face, and that explains on a very, very general level how the neural network and how deep learning works in general. So this term deep learning, like many terms, are historical. it is defined as deep learning if we're using neural networks, and if we're using neural networks that are big enough, they have more than one layer. I explained those layers just before, so if they have one more layer, in addition to the input layer, that doesn't count, in addition to the output layer, that doesn't count. So if they have at least one more than one hidden layer, the processing layer, that's called neural network. So today we deal with about, let us say, 5 to 10 layers inside. These are very complicated and computationally intensive tasks. It takes maybe 2 days on a cluster to train. Here are the examples of what people are able to do. That the Facebook Deep Face recognizes faces at least as good as humans. Google Translate works pretty well. The DeepMind plays Go, and that's a complicated game, and IBM wins Jeopardy. Well, so what's the practical advice? Andrew Ng, the founder of Coursera, professor at Stanford, his advice is that that's great, guys. We are in the beginning of this revolution where you all can take part. Do this. Read the paper and find a paper that you like. Replicate those results. Do not just read it for fun, but try to program whatever it tells you it did. And today you have a lot of different choices of how to do it. I'll touch on these choices a little later. Well, and after you do 20 to 30 papers like this, you will be quite an expert. Well, there is a different approach. They don't quite contradict each other, but Thomas Mikolov, that's the guy who invented the foundation for modern Google translation. That's a software library that converts words into vectors. And these vectors, they have very high dimensions, for example, 400, 500 elements per vector. So you can convert your word text to something very impressive. And he says, well, stop doing this. It's enough. It says every person comes to a conference and essentially builds another cat picture recognizer. Do something more fun. Do a system that will learn by itself and that will then learn how to learn. That would be much better. Thomas Mikolov went to Facebook for that because he felt that that's the place to do such kind of research, and he estimates 5 years that it will take him. And if you look at the latest ideas from Google, you'll see the same. You will see Jeff Dean, that's their artificial intelligence leader. He also says that one of the tasks they're working on is how to take a machine learning expert out of the equation, give it much more compute power, and that's in the future. That's not today. Everybody says 5 to 10 years. We'll see how that works out. Now back to the ground, back to Earth. Here is what you would practically do. You would say, well, first of all, there are 2 types of machine learning. One is called supervised, the other one is called unsupervised. In supervised, I'm telling the computer the answers that I expect. For example, I'm giving it all the faces, but I'm saying who is who. I'm giving it all of the house pricing, but I'm also saying, and that's what it really was sold for. So not only the house parameters, but also the prices are given. And there are many more examples. That's the most popular type of learning, where you give it the answer and then you're saying, now come up with a similar answer, or come up with a good, great answer. By the way, machine learning for self-driving cars would be in the class of supervised learning, because we do know what the driver should do. Unsupervised learning is where you do not know the answer, and in fact there is no answer, but you are saying to the computer, could you make sense out of that particular set of data? For example, could you divide all the data into clusters? Could you tell me that there are essentially 10 groups of data here? And even though I don't know what these are, but you, the computer, you should be able to find the trends. In this area, you have anomaly detection, something that's way out of the ordinary. Any other clustering, for example, they use it in medicine, they use it in news classification, and so on. And there is a little somewhere in between where you have some of the labeled data and most of it is unlabeled. That will be semi-supervised learning. So that's the basic vocabulary that we need. And with that, we can have some illustrations. For example, here is supervised learning. What we do here is that we have, let's say, house prices or stock market. We want to predict stock market, but we can go back years and years of training our model on the stock market. Or we can do classification. The difference between regression and classification is only in the type of output. In regression, you expect a continuous output. In classification, you want a category. For example, you want to say fraud or not fraud, or you want to say spam or not spam. So that's all in supervised learning. Here are a few more examples. For example, house prices that I was mentioning all this time, or present a face and the computer should tell the age of that person. Regression is where we get continuous out. Classification is where we're saying, here's the picture, tell me, is it a cat or a dog? What would be the practical application of the classification algorithms? Well, I mentioned web. Is that email spam or is it not? Then in medicine, is it a cancer or not cancer? In finance, you can do character recognition this way. So there are many practical applications. There are a few variations. Not every method is the same. And for example, decision tree is a completely different approach. In that approach, I want to show you, here are my decisions. So instead of giving you opaque, unexplainable result, I will say, here is the question you should ask, and based on that, you will arrive at the solution. So here I would present computer with all of the data, all the outcomes, and it will build a nice tree. It has its own advantages. That method will allow me to present as diagram to the management board. They will see what it means. It has some disadvantages because it may change. If I change the data a little bit, this decision tree may change a lot, but it's nice. So practically what you do is you collect your data, and that takes some time finding where the data is, doing it in the right format, in the format that the methods all expect. And then I need to do this. I need to train my data. I need to have a model that predicts. But I also want to test it before I use it in real life. So testing is done on a separate set of data. That set of data is not included in the training, and the computer doesn't see it. When it begins testing, it verifies, well, how well did it perform on the testing set? And then you keep tweaking this until you get a reasonable performance both ways. Then you can start using this model in real life. Here's one important consideration. Software would usually work more or less. You know, most projects are successful in the sense that the software works the way it was intended or close. In machine learning, well, you need a certain precision in the model. Let's say you get 63% recognition of something. That is very low. Most likely, that will not be practicable. And so I've seen cases where people collect the data, train the model. Alas, it doesn't give them the precision that they're looking for. Well, that's how data science is different. You're trying to find something. Well, if you don't find that something, then you continue looking. Unsupervised learning is different. I'll show you an interesting problem. Let's say it's called a party problem. At the party, there's lots of noise. People scream and dance, and or maybe just talk very loud. So you're telling the computer, can you find a group of sounds that relates to that particular person, or maybe to that particular music? Can you hear just that? So it would be an interesting problem, and it is a solved problem. Other cases is where you can group the document by certain characteristic, or somehow it would figure out which characteristic is important. Anomaly detection and so on. That would all be, I don't know the answer, but I want you, the computer, to help me. These are the major methods people use. You don't have the labels. Labels are the answer. So you don't have those labels, but instead You can use some clustering method. You can use some probabilities to guess what happened before. You have the state currently now, but you need to know what could possibly happen before. And these are all of the applications. For example, Google News could be one good example of this clustering technique. Here's how clustering basically works. We're trying to find good clusters. In this case, it's pretty obvious because we colored them. If I didn't put any color, then even here, the answer would not be all that obvious. And all the more to the computer who doesn't even see pictures. So that is a separate problem, and there are very many different algorithms to do this kind of clustering. The results are nice because you can use that for, I mentioned web, I mentioned cases where you're doing market segmentation, and then you approach each market segment differently and separately. In medicine, you can do that kind of clustering for image analysis and so on. Here are all the applications that could be used. Okay, so that's a summary. After all is done, you know, here are my algorithms. That's what the algorithms are good for. You can always go back to this table and find out what algorithm I should try. That's a complete cheat sheet that will allow you to run through your question, and it is even organized as a tree. So you can start from the center, and then is that involving deep learning? Then you go to the left, and so on. Now, practically, what are the technologies that I mean, I'm convinced I want machine learning. How do I go about this? Here are the very first easy choices. There are a couple languages that are well designed for that kind of investigation. The first one is R, and that is a language that is popular with college students, with data scientists, and you have thousands of libraries. You can start looking at your data set, quickly summarize the result, try to make sense of it, and build a model to say, well, it looks like a linear dependency, or it looks like a probabilistic dependency, and I can figure out what the probabilities are. Python is the same way. It has lots of very nice machine learning libraries. Well, one little problem with both is that they would have to fit your computer. So if you have more data than your computer can hold, then they cannot work there. So now there are also other languages and libraries, and some of them do work on a distributed environment. For example, a Python, there is a version that works inside of Spark, and it works in a distributed environment. The same goes for H2O. That's one of the libraries that concentrates on machine learning. And as I mentioned, TensorFlow exists on a single machine, but it also exists in the distributed environment like Spark or in the cloud. So here at the bottom, you have all the cloud providers. The cloud providers package those algorithms. The largest is probably still Amazon, even though some people will say, well, Google is great. It is true, Google is great. But it is only 4.5% of the cloud market. So as my friend likes to say, well, it's like Windows and Linux. Linux may be a great operating system. It may be better. Well, how many people use Linux nevertheless? So that's not that many, right? You need something else, not just the wonderful product. So I wanted to specifically mention SageMaker, and I'll show you what that is later. But here are all of the other libraries. You can do machine learning on Spark, and it's up to you where you get the Spark cluster, or you can come to Amazon Machine Learning and do it there. They have just come out with this SageMaker, which is a bunch of templates. It doesn't do magic, but it does a lot of examples, and that's where the power comes from. Then, of course, there is Azure and machine learning there, and then there is a separate H2O, very powerful company. So there are lots of offerings. Once you decide on machine learning in general, then you can learn machine learning in general. That's still the first step, and then specifically use a given library. Here are all of them. Usually when I present this, I ask guys, well, here's your example. Let's say you have a problem, personal problem, and you want to present some flowers. So where would you get the data for that kind of investigation? Where would you verify the data? Or let's say you are a business, medium-sized business. So the question is, what should you set your price for? Where would the data come from for pricing? What was good, what wasn't good? What were the results? But here instead, I want to show you something else. I want to show you what it would look like if we go to Amazon and if we run SageMaker there. And the way I will do it is this. That's, of course, there is kind of a little involvement here, and that is because that's one of the courses that I'm teaching, SageMaker. So I'll show you what you would go through if you're doing this same machine learning on the SageMaker. So here it is, solutions. Okay. So let's see. If it doesn't open from here, then I'll open it from a different place. So give me a second, I'll know what to do. So here in SageMaker, that's what you would be presented with. You would have a template, and that template contains code down below. There is code right here. And it will also explain to you the introduction. So my personal opinion that this is awesome and great for people who already know machine learning. It's not all that easy if you don't. In my case, I'm teaching exactly that. So I prepared this to show it to people. I'll tell them that this is the application of a new method called factorization machines, but all it does is detects classes. For example, in this case, it will be handwritten character recognition. It will be a digit, and we will figure out if that digit is a 0 or no. So you will include a place for your data. That's where the data is in your specific case, and that is my bucket. Amazon bucket is what is private to me and allows me to store the data. Then I'll tell them that, look, this is how you open the given data set. This is how you are looking at your first initial data. Then here is the data that you want to verify. That looks like a 3. It should come as a 3. And therefore, is it 0? No, the answer should be no. No, it's not 0. This is the code that you would run. And that is what I'm showing you is called Python notebook. So in the Python notebook, after you run the code, you get the answer. In that case, the answer was 0. Then the next step is load this model. Here is the output of the model. Then I'll continue with the code. Then it runs. That's the training part. In the case of Amazon, the question of where do I get my computer to run is answered. The Amazon starts another server for you. In other cases, you might have to provide that server or run on your own machine. In the end, we'll figure out, so what was the prediction? And the answer is no, it's not 0. Great. And then let's run it on multiple cases. So we should have a big number here, that's correct recognition, and a big number here, that's correct recognition of false. And then in here, we have the errors that made a mistake here. So we see some percentage of errors. Okay. And finally, Amazon allows us to put it into practice. That's called the endpoint. Endpoint is that server that stores the model. And then whenever we need to run it in real life, we will refer to that server and we'll say, okay, so now here's my data. According to what you learned, what is the answer? And that would give me the answer. Well, now I don't need it, so in this case I delete it. That's the practical application. So I showed you everything from the very beginning of here is what machine learning can do for you to the very end as to what are the technologies and practically how do you do this in the case of Amazon SageMaker. There are other libraries that also exist everywhere. Here we examine of potential features. Where would you find this? And that's kind of a mock lab that we're running. So just to check you, I know you don't have to answer, but just to check your understanding. If I would ask you, what is machine learning? How is machine learning different from regular programming? What would you answer? You can try to answer in this question and answer area, or you can try to answer just in your mind. I'll give you a second. And well, machine learning allows you to feed the data to the system, and the system will figure out what to do next, what the answer should be, as opposed to you program all the rules. If I ask you name a few cases of machine learning, then you could probably say, well, everywhere around, my phone learns my behavior, so it knows what I'm interested in, and then it sends similar things back to me. How does big data help in machine learning? I showed you that. Once you have more data and more compute power, then you get more precision, and that's how machine learning becomes better and better. Finally, if I ask you what is supervised learning and what is unsupervised, that's a more technical question. So the supervised learning is where you know the answers and you provide these answers to the computer. Unsupervised learning is where you're telling the computer to please figure out the structure of that data. All right, great. So that's pretty much it. I hope you enjoyed it and hope you got useful information out of that. If there are any questions, then the organizers will send me those questions. So far, I see no questions. So I'm all open. Please, if you have any questions on what has been happening here, then please, now is the time to ask. Wow, that's a wonderful question. What are the greatest challenges in artificial intelligence and machine learning? So it's not that I'm thinking, I'm waiting for the next question or the clarification. I don't see that, okay? So the challenges, that depends upon who we're talking to. If you are the project manager, then you need a good group of people, you need data, you need smart practitioners who know when more data will help or when it will not. So it's not that much different. If you're planning a project, not that much different from other types. But if you're a practitioner, if you're actually writing code or using code, then the biggest challenge is navigating in this wide area of algorithms, because they are all offered to you by different libraries, by different people, and this field moves very fast. For example, tomorrow they may come something like what's called hyperparameter optimization. So you need to find out what's that. And it turns out that it's additional help that you get after you choose the model. You can then stick multiple models into that same pipeline and try to run and optimize which model will it be. So I would say that the greatest challenge is exactly that. It is the latest and the most hyped area. So you would need to understand what's going on, what are the new offerings, when is the best use case for which algorithm. That's the very first thing. Then quick prototyping. It's very important to run fast and not waste 6 months on collecting the data that you are not even sure that it would help. So the next stage is, what do I do next? How can I prototype that in a week or two so that I see what kind of results will I get? And then finally, improving the model. Let's say you get 85%. Well, how good is that? Is that enough? Put it into practice. It turns out not good enough. No, I need another 9%, and I can get that if I go to a specific machine learning with neural networks, and I've seen such cases. So these are the outlines of what you need to do. You need to have a good grip on those technologies and then work hard to improve the quality. Okay, great. Next question. Which institutions and companies are the earliest adopters? Well, I'll tell you what I see, because I work with people who are adopters. So to me, they are adopters. And financials, the banks, credit cards, financial services, all these guys have cases that are already made for them. How can I improve my decision making? How can I predict that that particular person who is holding onto his mortgage will not defect or will defect? Should I contact him before he refinances with somebody else, or should I offer him money losing on my proposition, but it's still better than he churns out? So these are very clear use cases for finance. Another one is retail. Retail all the time, and they try to predict prices, create a model. The model tells you, well, these are the expected prices Monday through Sunday. So is there something unusual this week? If there is something unusual this week, then why? And can I create a better model to reflect what should be? So then once I have that data, I can predict what would be the better price. Okay, I'm happy there are more and more questions. What type of data? Well, here I would say the more data, the better. For example, usually you have at least 20 or 30 predictors. That's the very beginning, let's say pricing. But I want to know, where is this pricing happening? What store? What area? What's the zip code? What are the incomes of people coming there? So usually it is you're trying to get all of that data. You do not limit yourself to specific data, because whatever data it is, the algorithm will try to figure out which is relevant, which is not, and there are mathematical techniques to figure out which data is important and which one is not. So music in the sense of that business of music, then also yes. Oh, and we're dealing with all of these cases which essentially run as business, make money. So you can always get their data, plus you can also get the other data, the trends, that other store behavior, and combine it. The next is how much of statistical algorithm knowledge. I would say not that much to start, because let's say you open your data. It's a very simple spreadsheet in R. Well, it will suggest to you, well, it looks like you're dealing with a, let's say, Poisson distribution, because that is the timing that people stay in line, and that timing usually changes according to this Poisson distribution. So a good overview is fine, but you don't need to be very deep in stats. Implementing machine learning, that's a bit different, because here you need to first have a good grip on what the learning is. So I will say, if it is a course, then maybe it is 3-4 day course. If you're learning by yourself, or if you're learning only maybe an hour to a day, then it could be a month or two. And the practice, of course, once you start practice, then things will begin falling into place, because sometimes what you read or what you see doesn't make sense as yet. How would machine learning help to come out of mainframe? So let us say you have a system that's implemented in the mainframe and it's doing what it's doing. I think here, I mean, transaction processing, it's not doing any machine learning. So here I would say, well, first of all, I can implement some machine learning even on the mainframe. I can add something. If I would have to grab that data and put it into a better environment, well, then it would be a question. But if we're talking about getting out of the mainframe as a career, then, well, it's another technology. You would have to learn that technology. If we're talking getting out of the mainframe as an implementation, then it is the same question as can I get out of this mainframe and go into a combination of, let us say, NoSQL database and Spark, or maybe a search engine, which will give me certain advantages. So there you have your advantages spelled out. Plus, how much will it, how much effort will it be to implement some first machine learning results still on mainframe by exporting the data maybe to a powerful R machine and going from there. I think the questions are great, so we can always continue. You can always keep sending questions. What are the prerequisites to start learning machine learning? I would say one prerequisite is that you have a desire to be technical and you know some of the computer science or at least some programming language. Beyond that, you'll have to learn that or refresh the branch of math anyway, and it's a different way of coding. So, for example, you may choose to use Python or R or Scala. All of these languages are good candidates. And if you know any programming language, then usually you can either learn another one or find a good one which is close enough or that you already know that implements machine learning. So there is no prerequisite other than ready to do hard work and ready to do some programming. I feel that even if you are a manager on a project, then at least some practical experience will help. You will know much better what what you're talking about when you're conducting those meetings. Okay, so I think I answered all the questions that were offered so far.